University of Delhi. 25 years of teaching experience. Her research interest spans the area of database, stream clustering, classification, graph mining, social network analysis, and distributed mining algorithms. And next, I would like to introduce Ms. Kirti Jain. She is currently pursuing her doctorate in computer science from the University of Delhi. Her research interest includes network science and social network analysis. The third speaker I would like to introduce is Dr. Vasudha Bhatnagar. She has completed her doctoral studies from Jamia Millia Islamia, New Delhi, India in 2001. She worked in the Center for Development of Telematics as a software engineer, and currently she is a professor in the University of Delhi. So her broad area of interest is data analytics, and the current interest includes network science, social theories, time evolving graphs, and machine learning. Now, I would like to hand over this session to Dr. Sharanjit Kaur to start with her tutorial. Thank you very much.
Thank you. Now, I will request Professor Vasudha Bhatnagar to start the talk.
Thank you, Sharanjit, and thank you, Pooja, for the kind introduction. I'll just share my screen. Is my screen visible?
Yes, ma'am.
Yes.
Okay. Am I clearly audible? Okay.
Yes, ma'am.
Okay, so greetings of the day to all participants. I am Vasudha Bhatnagar, and I, along with Dr. Sharanjit Kaur and Kirti Jain, who are my research colleagues, we will be presenting this tutorial on modeling epidemic dynamics through contact networks. So, this picture about 2.5 years back would have evoked a very curious responses. About 2 years back, we would have thought, is this a woman sitting on chair, fiddling with a typewriter? Why is she wearing a mask? Is she a medico? Or why is she doing it? So, but today, if you show this picture to any primary school kid, that school kid would easily recognize, oh, she's wearing a mask because probably she doesn't want to get infected. She wants to keep herself secure from the epidemic. So the epidemic and pandemic in last 200 words, last 2.5 years has been a very, very common word in our, globally in our day-to-day conversations. So the topic of today's tutorial is very, very contemporary, very relevant, and I'm sure it is of interest to many computer science researchers. So this tutorial is divided into two parts. After a brief introduction, I will hand over the baton to Dr. Sharanjit, and she will discuss the differential equation based models which are used for epidemic modeling. And in part two, we will focus on the epidemic, how the epidemic spreads in contact networks. And towards the end of the tutorial, Kirti will give a demo and we'll also leave the script so that if anybody wants to try out the simulating the diseases, so that will be available on the GitHub account of Kirti. So we will leave all these details at the end of the tutorial. So why do we study the epidemics? In the last 2.5 years, it is abundantly clear that epidemics, they have a major impact globally on life and the livelihood of people. They affect the economy, global economy, and even at local level, they affect people. It affects even the policies and the politics of the country. We have all seen this very, very clearly in last 2.5 years. So it is important to understand that if an epidemic spreads, what is the dynamics of the spread? How does it spread? How fast does it spread? And in particular, we want to know, kind of predict, how long will the epidemic last, and how many people are likely to be infected. So we are just trying to make this predictions through the models. We also want to understand that how many people are likely to get hospitalized. So all this information, all these predictions, all these estimates are very, very crucial for administration of public health, managing hospitals, deciding policies, making provisions for healthcare. And they are really very, very important. These information, they form very important core of the for decision making. So before going into details, I'll just briefly tell you about how it all started. So we have known the epidemic only for 2.5 years. I mean, we have experienced it, and I hope and pray that our children never experience it in their lifetime ever again. The mankind never ever has to face. But that is only wishful thinking. We can only hope and pray. If you look at the history of the epidemics have been recorded even, in the before Christ era. So there is one science communication website called lifescience.com. That's a very interesting and it's a good website. So they list the worst 20 epidemics and pandemics, at the global level. With every epidemic, the society at that time, the scientists at that time, mathematicians at that time, they have always tried to figure out, can we make some predictions about the epidemic? The major success around in mid 18th century. So that was the time when smallpox was very prevalent in Europe, and they had just discovered the vaccination. But as we know, the vaccine for any disease is just a mild form of that virus, which is injected and into the body, and it leads to the growth of antibodies, which make us immune. So at that point in time, the vaccine that was developed was causing some deaths. So people were very hesitant. So Daniel Bernoulli was asked to model whether it is really beneficial to have the vaccine mathematically show. So that is the first evidence of a kind of thinking of a model for a disease. Then in mid 19th century, about 100 years later, cholera became a killer in London. So the cholera, as we know, it spreads by disease. So John Snow at that time, he studied the pattern, the temporal and the spatial patterns of the disease. And it is recorded that he was able to pinpoint the cause to the water source which was causing cholera. So that was a good contribution, and it was really a leap forward in understanding the spread of epidemics. Then a similar approach was used by William Budd, who modeled the spread of a couple of decades later. Now, the foundation of the compartmental models. Compartmental models I'm going to introduce. So, but these are just to give you an idea, these are the models which are prevalent for studying the spread of epidemics. So, the foundation of the compartmental models was laid by Ronald Ross, who was studying the transmission of malaria between mosquitoes and humans. So He got Nobel Prize for this work in 1902, and he showed that as the population of mosquitoes falls down when the winter comes, the malaria cases also fall down. So that he was able to analyze, and that was a big advancement forward in understanding of the spread of disease. Little later, Hamer was also able to, he figured out that the epidemic spreads is actually governed by how many people are susceptible and how many infected people are there in the population. And another 2 decades later, Kermack and Mandrick, they gave 3 seminal papers which founded the compartmental models. And they said that the compartments, they consist of individuals, right? And there are some susceptible individuals who are in one compartment. There are some infected individuals who are in the other compartment. And there is a steady flow of individuals between the compartments. And interestingly, all these models were developed not by mathematicians, but by people who were in public health. So that is an interesting, so I have listed down a reference, mathematical epidemiology, which gives a very, very interesting and authentic account of the studies related to the modeling of infectious diseases. So as I said, 3 papers, they set the direction of the form of the modern mathematical epidemiology. Now, the compartmental models, they are based on the concept that the entire population is in some compartment. So there is a compartment for susceptible people. There is another compartment which consists of individuals who are infected, and there is a third compartment. There is a third compartment which consists of individuals who have recovered. And these 3 compartments, right, they give rise to different models based on the biology of the contagion which causes the disease. Now, the simplest model is SI model. S stands for susceptible and I stands for infected. So this model considers only 2 compartments. So there are individuals who are susceptible. So susceptible individuals are those who are healthy individuals, right? So once a healthy individual comes in contact with an infected individual, the individual gets infected, right? So this was the first compartmental model. So this is the simplest compartmental model. Now, the next compartmental model was susceptible, infected, and susceptible. So this model is appropriate for diseases where after infection, the individual again gets healthy. And once the individual gets healthy, the individual is again susceptible to the disease. So like we have all experienced, like flu. In winters, there is a flu virus which is prevalent. So an individual may get flu, viral fever, recovers after about a week or so, but may get again infected in another 2 weeks or 3 weeks or more. So the SIS, susceptible, infected, susceptible model is appropriate for diseases where the individuals can get the infection. So the COVID virus, again, it is again a virus where the disease, once a person becomes healthy, can catch COVID again. So the COVID again is also belongs to this category, but it is more involved. So, and probably if we have time, we will discuss 1 or 2 slides on COVID if we have time. Now, the third more advanced model is for those diseases where once the person recovers, the person gains immunity, the individual gains immunity. So SIR stands for susceptible, infected, and recovered. So individuals in susceptible compartment, once they get infected, they move to infected compartment. The individuals in infected compartment, over a period of time, they recover, right? And once they recover, they gain permanent immunity. They do not get infected, right? So like diseases like measles or mumps, right, or chicken pox, where you get even the individual gets lifetime immunity, they can be modeled using SIR model. Now there's another category of diseases where the temporary is not, the immunity is not lifetime. It is only temporary. So like the immunity is there for 8 or 9 months, right? So like in COVID, it has been seen, it has been observed that the immunity is for about 6 to 8 months, and over a period of time, the immunity falls and one can get COVID again. So in this kind of a epidemic model, there are individuals in susceptible. All healthy individuals are susceptible. Once a healthy individual gets infected, the individual moves to the infected compartment, and once the infected individual recovers, he moves to recovered compartment. But then again, over a period of time, he goes to the susceptible compartment. So that means he's again is likely to catch infection. So these are the classical compartmental models. Of course, they're over a period, because these models were designed nearly 100 years ago. Over a period of time, there have been many improvements to, there have been many advancement in medical science, there have been advancement in mathematics and computer science, which have led to much more sophisticated variations of these classical models. Now, when we are looking at these compartmental models, now the question that comes to mind is, how do people move from one compartment to another? For example, a susceptible, how do we model the rate at which the individual moves from susceptible to the infected compartment? Now, the answer to that question is that it depends on the contagion, right? There are some diseases which are very infective, right? So in such diseases, the rate at which the individuals move from susceptible to infected is going to be very fast. And it is easy to relate. We have seen that there are certain variants of COVID which are very infective, right? So Delta was very infective. Now Omicron is also very infective. The earlier variants of COVID were not that, comparatively less infective. So this is about the movement from susceptible to infected. Now, at the rate at which the individuals recover, right, they gain health, that also depends on the biology of the contagion, on the pathogen, right? So that means in an epidemic model, we must have a provision by means of which we should be able to capture the biology of the contagion. Now, since we are looking at the rate, so rate is that means we are looking at the rate at which over a period of time, how many people are leaving one compartment and entering the other compartment. So differential equations, they can model this flow perfectly, right? So the earliest epidemic models, they use differential equations. Now, one of the caveats of the differential equation based modeling of epidemics is the assumption of homogeneous mixing. Now, homogeneous mixing means, so there is a compartment which consists of healthy individuals. There is another compartment which consists of infected. Now, since the population is together, it's a whole big population where the susceptibles and individuals interact with each other, there is equal probability of an individual, a healthy individual, getting in contact with an infected individual. So that means the compartments are large enough and there is a mixing of uncontrolled mixing of the members. So any healthy individual can come in contact with any infected individual. So that this is the assumption, this is a hypothesis, which is the basis of the classical compartmental models. The second assumption is that the disease spreads continuously and it is a deterministic process. Now we know that this is not true, right? The disease, it does not spread continuously, but in discrete time. So once the healthy individual comes in contact with an infected individual, right? The infected individual does not get the disease immediately, right? It is at discrete intervals of time. So maybe the next day, right? Or maybe a couple of days later. So every biological pathogen has an incubation period, because of which the disease shows up and the person becomes infective after a discrete interval of time. So this model is not very realistic. Now here, a very interesting, very true this is statement. It was meant by George Box. That was a very bold statement. So essentially, all models are wrong, but some are useful. So why he said that all models are wrong? Because no model can capture all possible realities of the world. So technically, if the model is not capturing the realities of the world, then it is not correct. But it doesn't mean that we should not model at all. Many of these models, they are useful because they allow us to approximate, they allow us to predict, they allow us to estimate some variables. So a model is as good as the assumption it makes about the real world situation. So the challenge in epidemic modeling, I mean, like any other modeling, the challenge here is, does the model, how realistic is the model? That means, so when we are modeling an epidemic, how many factors or how many components we are able to capture in the model? We know that in reality, the diseases, the people get infected based on their age, based on their health status, based on their nutritional level, based on socioeconomic conditions. So there are many factors. Biology of the contagion is one thing, right? That is one factor. But there are many other factors which affect the spread of the disease, right? So what happens in reality? So recall the assumption of homogeneous mixing, which says that the population of infected and the healthy individuals, that mixes without any condition. But what really happens in the beginning of the disease outbreak, one really has the population has only a small number of infected individual. Now that individual does not meet everybody in the population. That individual will probably meet only the contacts, maybe the family contacts, maybe the friends, or the office colleagues or so, and then he's likely to spread the infection only in a small set of people, not in the complete compartment of susceptible individuals. And so even if the person meets a number of friends, it does not mean that everybody will catch infection. because the immunity of all individuals is different. So the disease transmission in principle is not only discrete, but it is also a stochastic process. So there is a probability that the person a susceptible person, a healthy individual who meets an infected individual may or may not catch the disease. That will depend on the probability. So these are two really, caveats in the epidemic models that we use. So the differential, these are the main caveat, these are the two main caveats of differential equation based models, and these are the models which motivate to study how the infection spreads on the network, right? So the network models are also called individual based models. So the real world is actually a network. So a network, a person, an infected individual is likely to meet the direct contacts, right? So we can represent the network as a mathematical graph, right? Where all the individuals are the nodes of the graphs. And if two individuals interact, they are connected by the edge. So the mathematical graph G is a set of vertices. So that is all individuals, and the set of edges. Now the set of edges is determined by the interactions in this social network. Now this graph is undirected, which means either of the two individuals who are interacting can transmit disease. So the disease can possibly transmit in either directions. Now, another fact is that only when an infective and the susceptible individuals come in contact, then only the disease is transmitted. So essentially, we are talking of the epidemics are typically disease which spread by contact. So they are contagious or communicable diseases. So typically there are respiratory diseases, but there are some sexually transmitted diseases also. So now another reality of the world is that an infected individual interacts with healthy individuals independently of all other individuals. So the infected individual passes the infection as per the biology of the contagion. So that means if the contagion is very infective, then it is very likely that the healthy individual may get the infection. But if the healthy individual, even if the biology of the contagion says that it is very infective, if the healthy individual has a very good immunity level, may not catch the disease, right? So the network-based model of epidemic is stochastic and discrete time model. So at a point in time, so this individual is infected, right? Now he gets into contact with 1, 2, 3, 4, 5, and 6. He comes into contacts. He comes into contacts with 6 of them, but it is not necessary that all 6 of them will catch the infection. So this is a stochastic model. Now, so the network-based model, they are useful for they are more realistic. They depict more realistically how the infections spread. Now, the most interesting thing is that the information also spreads like an infection, right? So apart from the disease that spread, right, there are several other spreading processes which follow similar behavior, like the rumor spreads, right? So in rumor also, there's an individual who who passes on this information to the people or individuals to whom they are connected, right? So if I go back to this, so if this is the person who is starting the rumor or a gossip, now this person can communicate with any of these 6 neighbors, right, and pass on the information. But it is not necessary that all 6 of them will pay attention to it. Now, so only some of them may pay attention to it based on some probability, and then they can pass on this rumor to their neighbors. So the way the rumor spreads is very similar to way the epidemic spreads. So the gossip or the, the information on the social media and the politics or any information about the disaster, the spreading of all these follows a process which is very similar to the epidemic spreading. So this is studied under the area of information diffusion. Now, the computer viruses, Trojan horses, worms, they also propagate through connections. Now, so the machines are connected to each other, they communicate to each other, right? So a machine which is infected, so it can pass on the malware to other machines which are communicating. So that is how the virus spreads. So the spreading process for virus is also in principle similar to the process with which the epidemics spread. So this area is important for network security, and we study and people research about this. The network security researchers, they study how the computer viruses propagate and spread. Then marketing managers, they want to advertise, right? So how does the information spread, or how does the information about the information diffuses? So all these processes, the spreading of all these entities, right, is very similar. So that is why studying epidemic dynamics is not only limited to the study of diseases, but the basic principles are followed by many, many other spreading processes. So it is a very, very, very important and hot area of research. Now, when we are looking at the spreading processes, now what are the variables of interest? For example, if we are studying an epidemic, the government or the policymakers would like to know, can we predict for how long this epidemic will last, or how long this wave of epidemic will last, right? Or so if it is about information diffusion, right? If it's about information diffusion, then the person who is initiating the information, the diffusion of information, would like to know, in how much time can I expect that everybody knows about this rumor or the gossip or the advertisement, whatever, right? So the second variable of interest is the peak number of infection, right? So in case of epidemics, the health administrators would like to know, what is the maximum number of infections that can be caused by this contagion, right? So because they want to make arrangements for the healthcare of the public, for, and they want to, so we all know what happened last year, and it's not only in our country, this happened globally in many countries, where the predictions were, the actual number of infections was much beyond the number that were predicted by models. And there were the people of those countries, including our own, they went through a very, they went through a trauma. Then, the advertisers. So if we are looking in the context of viral marketing, the advertisers would like to know that if we start the propagation of information from this individual, how many people would get to know about this product, right? So peak number of people, the maximum number of people who are likely to get the information about the product is important for the advertisers, for the marketing people. Now, peak day of infection for epidemics is again a very important variable for the policymakers, right? So because they want to know, so how much time do we have to prepare and prepare the infrastructure? So all of you are aware how our governments, they raced against time to make arrangements for hospitalizations, right, to treat people. So peak day of infection is a very important variable. That so if the peak day is coming fast, then the government doesn't have much time to prepare. So they have to work with work under constraints, right? If the information is spread, if the epidemic is spreading slowly, then probably they have more time. They can make better arrangements and take care of the healthcare infrastructure. So what the point that I'm trying to make is that epidemic modeling is important not only for disease. It applies the modeling, the principles of the model, they apply to many other real life scenarios. So this finishes. I'm just looking if yeah, there are some questions. Let me just check if there's some questions. I think Sharanjit has already answered. Good. So now I will hand over the baton to Dr. Sharanjit, who will take up the next part, that is the differential equation based models. So any questions from the content that has been covered so far? You can unmute and ask. So we would like to keep this session, both the sessions, interactive. So at any point in time, if you have any questions, you can ask. You can unmute and ask the speaker. Okay, Sharanjit, I'll stop sharing the screen, and I think you can take over.
Okay, thank you, ma'am.
Okay.
I hope screen is visible.
Yes, ma'am.
Shall we do a control L? Yeah.
Yeah.
Thanks.
Yeah. So now in this part, basically I will cover how the differential equation based models are used for epidemic modeling. As Professor Vasudha have briefed you, what is the purpose of epidemic modeling, which type of models are there. So continuing with that, here I will be using some notations. Here ST indicates the number of susceptible individuals at any time T, and IT is number of infected person at time T, and beta is basically the transmission probability for the infection. What is the probability with which infection will spread from one infected individuals to the susceptible population? And K is uniform number of contacts which are assumed in differential equation based model, that from each individual is having K number of contacts. So in the population at time T, how many susceptibles are there? These are ST by N. N is total number of individuals in the population. So ST by N, it gives you the number of fraction of susceptibles in the population. And for the simplicity of notation, we will represent this as S. Remember here, we have also discarded T just for the simplicity purpose only. Then I refers to total number of fraction of infected individuals in the population at time t. So in the beginning, if there are n individuals in the population, so at time t0, we have n susceptibles. And when we have to simulate the epidemic spread, so that means there will be at least one individual who is infected. So we start with taking one individual as the infected person. And remember, K is same for all. So these are our assumption that at time T0, we are starting with one infected person. Now in susceptible infected model, there are two states: susceptible, who can be exposed to the infection, and I is individual who is infected. And from susceptible to individual, the probability of transmission probability is beta. Beta gives you the rate at which the transmission can be transferred from infected to susceptibles. So in this case, if we are assuming that individual is having K connection, then how many infections can be caused by an infected individual? Beta is the probability, K are the number of connection, then into S. So in these many individuals can be infected by any single infected person with whom any susceptible comes in. In this case here, through this infection, this infected individual, it can be spread. So rate of change, how many new infections will be there in time dt. So for that, because we have I is the fraction of infected individual, so the rate change in number of infected individuals will be beta into K into S multiplied by I. Remember, I is the fraction of individuals which are infected at time t. And we know that I plus S, this is equal to 1. So that means total population consists of individual and susceptible. And remember, we are considering that during this epidemic modeling period, we are assuming there is no birth and there is no death. So that is, we are taking here stationary population. So in that case here, infected plus susceptible, that will make n, that is number of individuals in the population. So in that case, replacing S by 1 minus I, we are left with beta into K into 1 minus I into I. So now when we differentiate it, in that case here, to get, we will come to know what is the value of I. So in this case here, when we will differentiate these equation 3, in this case here, we will get here the value of the constant we can find at the, assuming some certain condition, that is at time t0, if we take I as I naught, that is, this is the probability for the infection. In this case, this is the fraction of infected individuals. So in this case here, C comes out to be, after solving this 4, this will become logarithm 1 minus I naught. And when we will substitute this value in, when we will substitute this value in this equation 4, then we will come with this fraction of infected individuals in the population. That comes out to be I naught. Remember, I naught is the condition which we are assuming that at time t0, the fraction of infected individual is I naught. So in this case here using this equation 5, we can come to know in the population how many infected individuals will be there, where beta is the transmission probability, K is the number of contacts in the for each individual, and remember, we are considering it as a same for all the individuals. That is what assumption is being made for differential equation based model, and T is the time instance. So in this case here, for this SI model, here we now use one more new term, that is a characteristics time. What is characteristics time? Time is basically, it is the inverse of speed with which pathogen spreads within the population. Now, what is pathogen speed? How it will spread? It depends on the transmission probability, that is beta, and K is the number of contacts of each individual, either of the infected, in this case, because through infected, susceptibles will be infected only. So in this case here, beta K will give you how many new susceptibles will be infected. So what is the characteristics time? The characteristics time will be inverse of beta K, that is 1 by beta K. And why we are taking as 1 by E? Basically, in this case, to simplify this equation, equation 5, in terms of this beta and K only, here, this is the time required to reach 1 by E, fraction of susceptible is 1 by beta K. Now, if we see this characteristics curve of this SI model, in this case here we see two designs. These are exponential design and this is your saturation design. When I is small, in this case here, that is, here the fraction of infected person is small and susceptible population is more. In that case, infection will spread, and at the end, when the saturation is achieved, that means all are infected. In that case, there is no susceptible left, so that will comes to the saturation region. That is, no susceptible population is left within the individuals are left within the population which can be infected further. So that means here that when I approaches to 1, rate of change of infection will become 0. That is d by dt becomes 0. Now what happens? But in some diseases, now once any person is infected, then again it can become susceptible. Like in case of your common flu. In common flu, once we recover, then after 2 months or 2 weeks again we get infected again due to exposure to some another infected person. So this model is termed as susceptible, infected, susceptible. So susceptible will be exposed to infection by the infected individual with probability beta. And then once any infected individual becomes recovered from this infection, then it can again become susceptible. So where mu is, so that means here what will be the rate of recovery of individuals who are infected. So that is mu. That a new parameter is considered here, that is mu. That is the rate at which, the probability with which infected person will recover from the infection and again will be mixed with the susceptible population, means it can be again infected. So mu is another parameter, that is the recovery rate, and beta is basically the infection probability, that is the probability with which one infected individual can infect another susceptible individual. So now, because in this case we have two states are there and infected individual can again become susceptible. So in this case here, at any time, as we have seen in SI model, we have beta into K into 1 minus I into I. That is from the susceptible infected model. But because now in this model, infected person can recover with probability rate, that is your mu. So in this case, minus mu I will give you the number of infected who can be recovered. Mu is your recovery rate. So that means at any time, in this case, in my system, these many changes will be there in terms of infected individual. So again, when we have to solve it for the I person, that is fraction of infected individual. So in that case, we have to take some condition. So assuming again that at time t0, this infected person, fraction of infected persons are I0. Substituting this again in 6, we will have this equation, that is 1 minus mu beta K and this value. Now remember, in this case here, mu and beta K. Mu is the recovery rate and beta is your infection transmission probability and K is the number of infection. So basically here, on the basis of this mu and beta K, depending on this, we will have change in the infected person in the population. So this is the characteristic curve of SIS. That means in SIS model, some individuals keeps on getting infected and then they recover and then they can again go back to the susceptible individual. So in this case here, this change in infectious per person and the susceptible person in the population, it depends on beta and mu. So in the beginning, when the population is say n susceptibles are there, infected individuals are say I naught, I is small. So in that case here, the change in infection will be high. That is infection rate will, in this case, the infectious person in the population will increase, and at the end, it will reach to the endemic state. So what is the endemic state? That means here state where the number of infected and the susceptible individuals in the population stabilize. They become uniform. So in that case here, at larger time, I infinity means when the long span has been there. In this case here, at that moment, this will equal to 1 minus mu beta k. And how we get it? Basically here, in substituting this value, t is very high. So when this t becomes very high, this becomes the 1, and in this become negligible term. So in this case here, at the larger time here, the infected person becomes 1 minus mu beta k, and that is why it is termed as endemic state. So this model predicts here that pathogen will be there in the population, but it will be in the form that here basically there will be very less number of infected individuals and less number of susceptible individuals which will be exposed to the infection. But pathogen will persist in the population. Now, how to understand this term? Mu is a recovery rate and beta k, how this recovery rate and how this infections rate, how these can be related to each other. If mu is less than beta k, that means if recovery rate is very less compared to that of the infection rate, in that case, what will happen here? That is, everyone will be infected, recovery rate is very slow. So in this case here, and in this case here, the condition will be just like your SI model. But at time t infinity, in this case, endemic state will be achieved. That means some of the individuals will always remain infected, and this will termed as the stationary state. That is, at time t is equal to 0, t is equal to infinity, when last time has been gone. In that case here, we will have these many infected fraction will be there in the population. Then we have disease-free state. When we will have disease-free state, when the recovery rate is more than that of the infection rate. So in this case, fraction of infected will decrease exponentially and the pathogen will disappear from the population. This is only when the recovery rate of the individual, of the infected individual is more than that of the this infection rate which we have considered on the basis of k is number of the contacts and beta is the transmission probability which we are considering. So when we use epidemic model, there is also one more term which we'll talk about, that is the reproduction number. Reproduction number, that is R0. Now, how this R0, what is the meaning of this R0? So basically here, this R0 is basically computed in the beginning. It will give you the number of, average number of susceptible infected by any infectious person, considering all individuals are susceptible in the beginning of the epidemic, and it is taken as beta k by mu. So beta k is your infection rate and mu is your recovery rate. So when your R0 will be greater than 1, because you must have heard in COVID, during this COVID, we also listen about the reproduction number. The reproduction number is more than 3, reproduction number is more than 4. So basically it gives you the how that on average, how many susceptibles can be infected by a single infectious person. So when this R0 is greater than 1, what this indicates? That the virus will continue to propagate in the susceptible population, considering there is no change in the environmental changes. There is no change in the environment, no, that is death and birth. They are constant, no change in the population. Considering this, are not greater than 1 indicate that is disease will be spread among the susceptible population. but the pathogen will remain in the population, and depending on the value of this R naught, the severity of disease is computed. If R naught is greater than 2, that means on average, every infected individual will infect susceptible 2. Number of susceptible, that is 2. Wherever R naught less than 1, this indicates that recovery rate is more than that of the infectious rate. So that means at the end, virus will vanish from the population. So whenever this epidemic modeling is done, disease modeling is done, in that case here, we also talk about this reproduction number that is basically used by the epidemiologists to find out, to predict how much, in how many days, within how much time actually this infection will spread to how much of the population. Then we have, now as the disease symptoms are changes, then new models has been introduced. The next model was susceptible, infected, recovered model. And basically this type of model is used for disease where the individual gets immunity from that disease. Immunity system, in this case, individual develop immunities after recovering of that infection or that disease. For example, in measles, mumps, and rubella, here we cannot use SIR model. For that purpose, we have to make use of susceptible, infected, and recovered model. So that means here now we are introducing one more new state, that is recovered. So recovered, as the name indicates, that individual who will be neither infected or who cannot infect, that is, he has developed immunity and nobody can be infected by that person. And what is infected? Infected is a person who is in the state through which more susceptible individuals can get infection. So that means at the end, recovered individuals are removed from the population because they have attained immunity. After getting the infection, they have recovered from the infection. So that means initially what will happen here, the number of infected individuals will be small, susceptible population will be more. As the disease will spread freely in the population depending on the transmission probability, infected individuals will increase exponentially. So that means here the susceptible will be exposed to infection with transmission probability beta, and infected will recover from the infection with recovery rate mu. Remember here, see the difference in SIS model and SIR model. In SIS model, we were having the infected may be going back to the susceptible state. But in this case here, in SIR model, it is considered that depending on the disease, that once any infected person recover from the disease, then that individual is removed from that of the population. So the person may be dead or may has developed immunity system against that disease. So that means now at any moment we have three states, that is SRI. S represent the fraction of susceptible, R represent susceptible of recover, that R represent the fraction of recover, and I represent fraction of infected. So at any moment, all these taken together will give us one value because we are taking a fraction here. The sum of these fraction will be 1. That is a total number of, we are using here, that how many fraction of infected persons are there, how many fraction of, what is the fraction of susceptible individual, and what is the fraction of the your infected individual. So now in this case here, what happens, just like in case of SIS, the persons are being recovered. But remember, once the person are recovered, they are not going back to the susceptible state. So the rate of change for the infection is given as beta Ki 1 minus R minus I. See difference here. Now instead of 1 minus I, we have 1 minus R minus I because some person have been shifted to the transfer to the recovered compartments. And some of this, in this case, so that means at any moment susceptibles are not 1 minus I, that is 1 minus R minus I. And this indicates here the person who have recovered. So rate of change of recovery, this is dr dt is given as mu I, because I is the number of individuals. This will give you the fraction of infected individuals, and mu is the recovery rate. So the rate of change of your recovered individual is mu I. And the rate of change of susceptible, now this is different from your SI and SIM model. This becomes minus beta Ki into 1 minus R. That means these many susceptibles have been reduced from the population due to change in the state of infected individual and that of the recovered individual. So in this case here, we have, when we model this epidemic disease modeling using this SIR model, so we are actually considering three curves. These are susceptible, infected, and recovered. So as you see here, that in this, that is, there is, in this case here, decrease fall in the susceptible is very fast, and similarly, infected individuals has increased exponentially and then they decrease. And there is change in the, this violet line, this indicates the change in the increase in your recovery individual. This recovery individual, these are increasing. So once any person is in the recovery state, that it will not move back to the infectious state. So that is why it is increasing. And susceptible individuals, why it is decreasing only? Because when the susceptible person is exposed to infectious individual, then it will be changed to the infected state. So in this case, susceptible population is reduced, and then in this case here, it will decrease. So here, initially the fallout is exponentially, and then it decreases slowly. So that means at the end, this SIR model, it predicts that everyone will recover in the population. And remember, the change in this infected individual or that of susceptible individual, it depends both on the parameter recovery rate which you consider and the transmission probability which you consider. But nowadays, what happens that in addition to this SIR model, we also consider one more term, and that term we have also learned in case of COVID model. That is, individual is changed to exposed state. What is exposed state? In addition to SIR state, there is one more state, that is the exposed state. So exposed to infection means that person has been infected, but it is the state through which no other one will be affected further. No one can, or infection cannot be spread from this state individual in this state, that is exposed individuals. So whenever any infected person comes in through any infected person, susceptible is exposed to infection. So first of all, it will make change to exposed state, and then after this incubation period, it will move to the infected state. That means here that the person has got the infection, but it cannot transmit it. Within say 2 or 3 days, it cannot transmit. But after this, the symptoms will appear and infection can be spread from that person. Then just like in SIR model, recovered individuals are removed from the population as they have developed immunity after recovering from the infection. So initially, just like in SIR model, initially the infected persons are few. So disease will spread freely because number of susceptible individuals are more. And with time, the number of infected individuals becomes large and they become stationary with time as the susceptible population will reduce. And this rate of change on infection will be exponential in nature. So as this diagram show you that now we have 4 states instead of only 3 states or 2 states. We have susceptible population, individuals who are healthy, who have not got infection yet. But when in this case here, whenever they will come in contact with the infected person or through the infected person, they will get the infection. So in that case here, they will first move to the exposed state. Exposed state, as I have told you, is the state where it is, we can say here, the person has got the infection, but the person cannot infect another person. It will take some time. During this period, more symptoms will be there, and then the person will get infected. And from E to I, they will convert with probability beta. And once the person is infected, in that case, it will be removed from the population using recovery rate. So now in this case here, we are talking about 4 types of individuals. So we have 4 states: susceptibles, exposed, individuals, and recovered. So in this case here, as you see here, that is the rate of change in susceptible is slow compared to SIR model. If we say the diagram of SIR, in this case, its change was very sharp. But in this case, it is slow because there are exposed states is also. And the exposed state, it increases and then it decreases. Similarly, the change in infection, that is slow compared to SIR model, and then the infected individuals, they increases and then they decreases with time. So remember, in this case here, see the difference of this red curve. These are the exposed individuals. Exposed individuals are basically, these are the persons which have caught the infection, but they have been exposed to the infectious person, but they cannot spread the infections. So they will not take part in spreading the infection as that of the infected individual. So in case of SAIR, in case of COVID, now in last 2 years, different models have been proposed based on this SAIR. We now talk about asymptomatic infected individual and symptomatic infected individual. So that means this model has been extended further to handle the various pathogen characteristics of this coronavirus. So in that case here, we see lots of models, differential equation based model, including different states depending on the characteristics of the pathogen. So at the end, what we can get from this, that differential equation based model, they model this rate of change in infection, rate of change in susceptible, depending on the crucial parameters, that is your transmission probability and that of the recovery, as well as depending on the characteristics of the pathogen. Different compartments can be added and then it can be modeled. This disease can be modeled. But what is the problem? What is the limitation of this differential equation model? As it seems to be very powerful, but the limitation is here that in this case here, homogeneous mixing condition is assumed here. That is that everybody has equal chance of getting infection. Every infected person will exactly, in this case we are assuming exactly it has it will infect K individuals. That is, we have same number of contacts we are assuming, but in reality it is not there. Everybody has different number of connection. In our contact networks, one may be coming in contact with 2 person or 3 person or 4 person, depending on the area where that infected person is moving to. Say person is infected and he is moving to his workplace. In that case here, the contacts will be more. And if he is at home, then contact numbers will be different. But this thing is not handled by differential equation based model. So for that purpose, we have to model these epidemic models on the contact networks. We have to consider, we have to generate contact network as per the underlying population, because the population may have different heterogeneity in terms of degree, in terms of contacts. So that we will cover in the second part. So if you have any doubt in this, you may please ask question. Any question, please?
The participants can even unmute and ask.
Is there any doubt, any question? Yes, there is one person who have raised the hand.
Can I talk? Good morning.
Good morning. Here is good
All right.
evening. Yes.
Yeah, thank you for your lecture. It was very interesting. I am calling from Bangkok University, Nigeria. My question is earlier, the exposed, but I found out that later it was captured in the model of this SCIR. Because from our perspective here, it is possible for someone to be exposed and still not get infected. Possibly that is why we say maybe he's having a immunity towards the disease or towards the virus that is trending at that particular time. And again, we can also consider if there are other factors why the person might be exposed and not been infected. So if we distinguish between the susceptible and the exposed in the model, there is still something we can actually bring up from there.
So I think you are asking about the difference in exposed individuals and infected individuals.
Yes, please.
Yeah. So basically, the exposed person are those persons who have got the infection, but they cannot transmit it. For some time period, they will not transmit the infection. So that is the exposed state. But after say 2-3 days, then more symptoms will develop and then they will start infected another person. So that is why this state has been introduced, exposed state. So that is a basic difference between exposed and infected. I hope it is clear.
Yeah, thank you very much. Thank you.
So now I will continue with the second part. So as I have told you that in this case here, what is the limitation of differential equation based model? That so what is the need of epidemic dynamics on network? Why we have to move? Why we have to do use networks for modeling the epidemics? What is the need? So in this case, what was the problem with differential equation based model? That the modeling, the disease or the variable which they are capturing, they are not realistic, because in the reality, in the population, individuals do not have equal number of contacts, and chances of getting infection is not same for everyone. It will vary. It will depend on the condition where two persons are meeting, whether the person that particular place is crowded or not. So depending on this here, these models, differential equation based model, whatever the variables they are predicting, they are not realistic. So in order to overcome this limitation, although these differential equation based model, these are very powerful, but due to these two assumptions, there are different types of methods have been adopted. One is your network based epidemic model. Nowadays, what happens here, the network structure basically is being used to represent the contact pattern within the populations. And using these contact patterns, this disease modeling is done. And through these contact patterns, actually, and we know in reality in COVID, we have seen, we have learned that we were trying to avoid connection with each other. Because in this case here, we were told that infection spread through contacts. So minimize the contact, don't move outside, stay at home to avoid the spread of this pathogen. So in this case here, because of this reason that the infection spread through the contacts, we were avoiding the contacts. And to capture the real contact pattern in the population, we make use of contact networks, and we have generative models through which we can construct synthetic network to mimic the real world connection. So in that case here, network dynamics, these are being actually modeled through the contact networks. And remember, this network dynamics, that is number of infection, the peak day, epidemic span, all this will depend on the network topology, that how faster infection spread. Remember, we have different types of contact network. So depending on the contact network we are using, we will have different values of epidemic variables. So in real life, so now we will talk about what is the meaning of the network topologies, how we can create synthetic network which can mimic the real world population contexts. In reality, the networks are large and sparse. Sparsity means, in this case here, that if we have 10 nodes in a network, there are 10 individuals in the population, then everybody is not connected to another one. One will be connected to another second person. There will be two connections with one person and so on. So basically here, all of these networks, they differ at the microscopic level. But when we have to build these contact networks, we talk about 4 major structural properties. These are called small world properties. Small world property, basically in this case, we say that is the distance between two individuals is small. That we will do in detail. High clustering effect, that is how the neighbors are, or my neighbors in my contact patterns, they are connected, whether they are known to each other, whether they are friends with each other, whether they will meet with each other. And then real world network, there is no disjoint components. Then scale free property, it says here that there are very large number of nodes with small degree and high degree nodes. These are very few in the population. So let us talk about these macroscopic structural properties and how they affect the epidemic spread on the contact network. So what is a small world property? Small world property, basically it is described on the basis of average shortest path length between pairs of node, and it is associated with 6 degrees of separation. In this case here, basically what happens here in 1929, this idea was first floated by Frigyes Kirti. In this case here, that everybody in the world is away from each other 6 or fewer steps, not more than 6 steps. And again, this concept was basically popular in a play written by John Bury. That means in this case here, everybody can be reached to another part of the world within 6 steps only. That means if I will start from this, then to other part of the world, I can reach in 6 steps only. So at the most 6 steps are required to move to another part of the world. So that is called here 6 degrees of separation. Then recently in 1969, there were researchers at MIT lab. They again conducted this experiment, and then they found that there are contact social network. In this case here, this path length, average path length is lesser than this 6 in number. This is actually 3 or 4. So they concluded that this human society is a small world network which is characterized by average short path length, which is maximum 3 or 4 in number. So a graph, a network which exhibits this small world property. When this network is said to follow this small world property, if the average path length mu scales logarithmically with number of nodes, means if I will have log 10, log n is 10, so that means average path length is log 10, that is 1. So if by this number is n is 20, then average path length will become merely more than 1, and so on. And if it is 100, only then this average path will approximate to 2. So that means here, even though the number are increasing, they are doubling. But in this case here, the average path length is not increasing as much. So that means our real world follow this small world property. Then another property is clustering effect. That means this clustering effect, this basically used to capture how my neighbors are connected with each other. How dense is my neighborhood? For that purpose, we talk about this clustering effect. So what is clustering effect? For that purpose, we capture clustering coefficient of a node. So what is clustering coefficient? Like, let us consider this diagram. In this case here, we have 8 nodes, V1, V2, V3 up to V8. Now V1 has 4 neighbors, V2, V3, V4, V5. V2 has 3 neighbors, V1, V5, V6. That is, V2 has 3 contacts. V4 has 4 neighbors, V1, V3, V5, V7. And V8 has only 2 neighbors, V7 and V5. So what does this clustering coefficient says? So this is basically, this is the probability that 2 randomly selected friends of a node, these are friends themselves. And how this is computed? This is computed on the basis of actual number of edges within the neighbors and maximal possible edges within neighbors. So in this case here, if we take this neighbor V4. So in this neighbor has 4 contacts, V1, V5, V3 and V7. And in this contact network, only V1 is connected with V3 and V1 is connected with V5. So this is basically the induced graph of V4 is this V1, V5, V7, V3, and the contact within the neighbors are V1 and V3 only, and V1 and V5 only. So what is the number of edges in GI within the neighbors? This is your 2. And maximum possible edges within the 4 neighbors, this is 6. So this becomes 2 by 6, that is 0.33. That is the clustering coefficient of V4. So if I say here that what is the clustering coefficient of V8? It has 2 neighbors. As there is no edge between these 2 neighbors, so clustering coefficient of V8 is 0. That means these neighbors are not connected with each other. So in this case here, clustering coefficient, it gives you the idea about how densely my neighborhood is, how my neighbors are connected with each other. And depending on the clustering coefficients of the neighbor, the clustering effect of the network is determined. For that purpose, global clustering coefficient is computed by taking the average of the sum average of the clustering coefficient of each of the individuals. So when a network is said to have high clustering effect, a network is said to have high clustering effect if this clustering, the average clustering coefficient is significantly high compared to edge density. And what is edge density? Edge density of the network is computed as actual number of edges in the network divided by total possible edges in the network. If this clustering coefficient, average clustering coefficient is high compared to the edge density, then we say that clustering effect, this network has high clustering coefficient. That means the neighbors are connected with each other. Then the third property is your scale-free property. And this scale-free property, this is computed on the basis of degree distribution of the nodes. Degree distribution of the nodes means what is degree? That is, in this case here, V1 has degree 4. V4 has degree 4. So that means there are 2 nodes. Then we have V5 is also having degree 4. 1, 2, 3, 4. How many nodes of degree 1? There is only 1 node of degree 1. How many nodes of degree 2? There is only 2 nodes of degree 2. So what we'll do, how we will compute degree distribution? Degree distribution is computed on the basis of, let me first, in this case here, for computing the degree distribution, what we will do, we will compute the frequency of each degree, degree 1. In this case here, for degree 1, we have only one node of degree 1, 2 degree nodes. In this case, we have 2 degree nodes are 2 in this network. How many 3 degree nodes? 3 degree nodes. In this case, we have VV2, that is 3 degree node. Is there any other? Only, I think there is only one node of degree 3. Then we have node of degree 4. Node of degree 4, we have V1 degree is 4, V4 degree is 4, and V5 degree is 4. So we have 3 nodes of degree 4, and so on. So we will compute the frequency of each degree. In this case, what is the maximum degree? The maximum degree is, here V5 is also 4 degree. So maximum degree was 4. There is no node of degree 5. No, there is no node. So in this case here, 0 degree node is 0, that is no disconnected component. 1 degree node is, we have only one node whose degree is 1. In this case here, there are 2 nodes of degree 2 and so on. So that will give you the degree distribution. And this scale-free property, it works with this scale-free property, it works with degree distribution. And according to this degree distribution, that is, there will be large number of nodes, that is frequency of nodes with smaller degree will be small. In this, there will be large number of low degree nodes and few very high degree nodes. So very high degree nodes, they are called basically hubs. Their connection is very large. Number of connections are more. So this power law or this scaling law, this is used to describe a phenomena, that is small number of items are clustered at the top or the bottom of the distribution. And this phenomena is seen in real life also. When we talk about the income distribution, there will be large number of people with average salary, and high income persons will be very small. Frequency will be very low. Similarly, we talk about in case of word frequency. So power law distribution, as this shows here, that is here the last, if we take it as a salary distribution, low income persons are very high, but as the income increases, here the frequency decreases. So this is your power law distribution. So this scale-free properties, this is defined using the power law distribution. So that is, there are very few hub nodes and very large number of small degree of nodes. And this empirically, this degree distribution, which is represented as Fk, it follows scale-free behavior. And this distribution will have long tail distribution. Why long tail distribution? Because higher frequency nodes which are very small in numbers. And they call a power law relationship, which is represented by Fk approximated by K exponent minus gamma, where gamma is the exponent for this power law distribution. So in this case here, so in real life, also the social contact network, they follow scale-free property. That is, there will be very few individuals which will have a large number of connection, but large number of people with few contacts, very small number of contacts. This is showing you here the logarithm plot of the social contact network. That is, this is showing you the degree distribution. So if we take the log plot of this power law distribution, it comes out to be the straight line. So in this case here, on the x-axis we have the degree, and on the y-axis we have the y-axis. So degree distribution in any social contact, now nowadays when we talk about Facebook networks or we talk about WhatsApp network, in this case here, if you follow the connection pattern and if we plot a degree distribution, it comes to be this scale-free property. It follows the scale-free property. That means degree distribution of individuals follows power law distributions. So on the basis of these properties, and in this case, one thing which we are assuming here, when we use these networks for modeling, we assume that there is no disconnected component, means everyone is connected with each other. So that is, there is one component only. So that is why we have not talked about disconnected components. So first network which was used for modeling this simulation for epidemics, so that is here random network. Now, in random network, basically, the networks here, the heterogeneity within the degree is very small, and this follow the Gaussian distribution. Path length is short. That means here it follows the small word property, but the clustering effect was very, very small. That means here the neighbors connection was very small. And this type of random network, this was first given by, this is basically this model we can, this type of network we can generate using the Erdős-Renyi graph model. So in Erdős-Renyi graph model, in this case here, the degree heterogeneity will be very low and it will not follow the clustering effect. But in reality, there is a clustering effect. Within the connection, my friends are also connected with each other. So in that case here, the new model was introduced by the Vasudha, which considers this the missing concept of clustering coefficient. Again, in this model, the low heterogeneity of nodes were there. Among the node degree was considered. Short average path length means small word degree property was followed. In addition to this, high clustering coefficient network with high clustering coefficient can be introduced. And this model was first given by Vasudha. So the graph model which is used to generate this small word network which follows the clustering effects and that of the small word property, these networks are called small word networks. But after some time, then Barabasi, they have proposed that in reality, like if we say the online social networks, in those networks, there are some nodes which are highly connected. Although they are very small in number, but they are very highly connected. So their degree is not comparable with the degree of the rest of the nodes. So in that case here, so these two networks, random networks and small word networks, they were not actually following this property. So in that case here, there was third graph model, which was introduced by Barabasi, which is called here Barabasi-Albert graph model, where the heterogeneity in degree was considered. Means very large number of low degree nodes can be generated and very small high degree nodes, that is hub, can be generated, which follows the long tail distribution. And such that they follow the small word property, but model which is network which is generated by using this Barabasi BA graph model, Barabasi-Albert graph model, it was very low in clustering coefficient. So again, this model was further enhanced so that the real life clustering coefficient property, the small word property, it can be induced. So using these variation in these different graph models, actually nowadays we can simulate the connection pattern within the real population on which we want to simulate this disease dynamic. So this basically, this diagram, this table, this consolidates the properties of three types of networks: random network, small word network, and scale-free networks. So all these three types of networks, they follow the small word property. So what is the small word property? That means there is a average path length between any two nodes in any two individuals, wherever they are, is not more than a quantity. And nowadays, using the Facebook or the social network, it is found it is not more than 3 or 4 in number. Clustering coefficient, that how my neighbors are connected. In random network, this connectedness within the neighbor is very low. But in small word network, clustering coefficient is very high. Clustering factor is very high in case of small word network. And the scale-free network, it has clustering effect, but not more than small word network, but more than that of the random network. And the scale-free network, they follow the power law distribution, whereas these random and small word network, they follow Poisson distribution, considering we are taking here the large population. So in reality, real world social network, they follow small word properties and the scale-free properties. So that means usually these small word networks and scale-free networks, they are being used. In some papers, they have also extended this random network to simulate the study of this disease modeling. So now, because we were talking about SI model, SIR model, and SIR model using the differential equation, that how we can solve, how we can compute number of infected individuals, number of susceptible individuals. Now we are doing this on the networks. So in networks, now we are considering here that each individual has different number of connection. So here degree block approximation is used to capture the actual number of contacts of individual, because there will be k in present here the degree. The 4 degree nodes, they are connected with another individuals. There is a one block of nodes with degree 2, they are connected with another individual. So here this one block, this represent individual with degree 1, this represent individual with degree 4, this represent individuals with degree 2. So here in this case here we are basically working on the blocks where the individuals are further divided on the basis of the degree. So that is in addition to SIR compartments. Now we are considering here one more compartment, one more block, that is in terms of degrees. So because 2 nodes with same degree, they are statistically assumed to be equivalent. So that is why they are considered, they are placed in one compartment only. So now we are not talking about I only. Now we are talking about the fraction of individuals with degree K and fraction of individuals with degree K. So in this case here, what is how many individuals who are infected are of degree K will be given by IK by NK. And because we are considering here different compartments on the basis of this degree, so we have probability also associated with this degree also. So that is why we are having total fraction of infected individuals I is equal to summation of PK IK, where PK is the probability of node with degree K. In differential equation, how we have mapped this rate of change in infection, this was mapped by beta into K into 1 minus I into I. And remember that this 1 minus I, this represents the fraction of the susceptible individuals. So in case of networks, how this will be represented? This will be represented as beta into K into 1 minus IK into theta K. Where, what is this theta K? Theta K is basically the fraction of infected neighbors of susceptible nodes of degree K, and is used for each value of K, that is degree K, because in network there are individuals with different degree. 1 degree node can be 10, 2 degree node can be 100, and so on. So in this case, instead of using average degree K in case of differential equation model, now this is done on the basis of actual degree. But now in this case here, they are considering one more compartment, that is compartment on the basis of degree. And here, remember, this is capture this theta K. This will actually give you the fraction of infected individuals of susceptible node of degree K. So now, once what we have done now I'm showing you here the networks which we have generated using these three graph models. That is, we have random networks, we have small world networks based on the basis of Stochastic model and on the basis of Barabasi model. We generated three networks. In the next part here, Kirti will show you how to generate these networks. In here, I'm just showing you how we are getting epidemic spreading over these three type of networks and how they vary. So we have created three networks, each of degree 30. And these are the edges in each network. So clustering coefficient, as you see here, small word network is having the maximum clustering coefficient. Then we have scale-free network. Then we have clustering coefficient of the random network. So random network has the lowest clustering effect. Wherever the small world property is being followed by all of these three networks. It is around approximately 3. That average path length of these network is 3. And the degree, minimum degree in random network is 1 and maximum degree is 7. In small world, this is 3 to 5. And in scale-free network, this is 2 to 10. And this is your degree distribution plotted for these three networks. As you see here, the degree distribution of this random network, this is basically approximately following because binomial distribution. This is normal distribution it is following. But as the number of nodes will increase, it will tend to the Poisson distribution. So that can be, we can approximate by using a single parameter. But if you see here the scale-free distribution, it is followed by a long tail of few values. So scale-free distribution of this network, it is following, approximating your power law distribution. Now, I will now switch over to the next video. Here, I will show you the simulation of this epidemic spreading over these three networks. And remember this simulation. Here, it is showing you how the connection, through this connection, actually, the spread is flowing. In assuming we are working on simulation using SIM model and using the 2 parameter values, transmission probability mu 0.2 and the recovery rate 0.1. So I'm switching to another PDF to show this simulation. So we have simulation for 3 networks. So I am starting with simulation for scale-free network. Why? Because in scale-free network, because this is follow the power law distribution, in this case, there will be rapid increase in the infected node. And wherever, in case of small word network, this infection spread will be comparably slow. So this is a scale-free network where these nodes, these 7 and these 2, they are basically very large degree nodes. And the rest of the nodes, as you see here, they are of degree 2, 1, 2, and 3 only. So maximum high degree nodes are 1 node 2 of, in this degree, they vary, degree was 15. So now I'm starting this simulation. So as you see here that with time, this red node, this indicates here your infected node, and then they become recovered. This green node, they indicates here the recovered node. So in the beginning, the change in from susceptible to infected, that is very fast. And with time, slowly, this infected individuals, they are recovering. So these green nodes, they indicates the recovered nodes. And these gray nodes, these indicates the susceptible nodes. Because we are showing you simulation for some limited dates. So these nodes have not been infected. So from this is your scale-free network. That is the increase in infection is very fast. And then slowly the infected individual will recover. Now this is random network. In network, we are starting simulation from one node, that is Here, this red node, that is we are starting from this infected node. And if you will see here, this in random network, the individual degrees, these are comparable. These vary from 3 to 5. And highest degree node is, I think, 4 or 5 in this random network. So here, from first day, 2 nodes are infected, then 3, then 4. So infection spreads slowly compared to that in your scale-free network. And similarly, the recovery of node is slow compared to that of your scale-free network. But so that means here the topology of the network also play an important role when you try to model disease. Whenever you try to model disease epidemic dynamics through the network. So network topology plays a crucial role. Now, let us see how this simulation varies with small world network. This is a small world network. In this case here, small world network, here the every node, approximately every node is having same degree. And there are these networks 28, 11, they are having degree around 5 and 6. And basically here, as you see that in this case here, infection spreading is slow compared to scale free and that of the your random network. In this case here, because here the connections are comparable, the connections are approximately same. So through this connection, because disease is being spreading, so this rate of spread of the disease is slow compared to that of your small world random network and that of the scale-free network. So now let us see the difference in terms of their infections, that how, as I'm telling you, that spread is different. So that we can understand through the curves only. So for that purpose, so I think my screen is visible to all. As I am telling you that in scale-free network, here the infection spread very faster compared to random and small network. So that you can, yes.
Yeah, screens are visible, and in your simulation, you took beta and mu values at 0.2 and 0.1.
Yes.
So any special reason for these values?
No, we have used the default value in the library, which we have used. We can change it as per the pathogen.
As per the pathogen?
Or the disease for which we are simulating this spread.
Okay. Okay, so for this you have taken 0.2 and 0.1. Is it random?
Yeah, this is basically we have just used the default value which we use in the library, not specific reason. There is no specific reason.
Maybe the change in these values have a wide impact.
Yes, yes, it will have. Like if we have say K, we are basically here comparing beta, K, and mu. So yes. In that case here, beta is basically transmission probability, K is the number of connections we are taking here, and mu is the recovery rate. So depending on the severity, like in case of COVID, recovery rate is very small compared to the infection spread. Oh, so depending on this, yeah, accordingly here, these values are taken, are used, and the epidemic is simulated. So usually, if we go through the literature, in this case, we will find that this beta value, they take value from beta 0.5, or at the recovery, they take as 0.2, 0.3. But recovery rate is taken comparably lesser than that of the 0.5, so that this simulation can be shown here.
Okay. Okay, I got it. So, thank you.
So during the demo, Kirti can show you how the variation of these parameters make a impact the curves, these epidemic curves.
Okay. Yes. Right.
So just remind Kirti when she's doing it.
Okay, fine. Fine. We'll do.
So in this case here, as you see here, that this red is basically representing the infectious node, and these gray, these are susceptible, and greens are the recovered node. So if you will see here that this infection rate is shoot ups very high in case of your scale-free network. And wherever the change is very slow in this infection, number of nodes are infected very slowly, and then they decreases. This is for your small world network. So that is why in case of recovery node, if you see here that the recovered node, they are approximately same in case of your random network and in case of your scale-free network. Wherever this is slow, change is slow in case of your small world network. And that depends on the properties which they are following. Depending on that, we have different values or different curves of this epidemic curves are there. We also plotted that to show the difference, that how differential patient based model, they are not assumed to be realistic. They cannot capture the realistic disease change compared to that of the contact network. For that, we plotted this differential equation based number of infection we have captured, and that we capture through the networks. So as you see here, that in differential equation, this rise is very sharp and then it becomes slow. Wherever in case of network, this change is very slow compared to differential equation based model. So that is why here nowadays this epidemic modeling, this is being done on the contact networks, considering the population density, considering their connections. We create network, and those network we model this epidemic dynamics. So in this next part, this Kirti will show you what are the another type of networks we can work on, and how we can simulate a network, this disease through the networks using different parameters. So if there are any question, you can ask, and then I will ask Kirti to carry on. Yes, Kirti, now you can start.
Thank you, ma'am. Good afternoon, all. I will be covering the community structure network part and the demo of the epidemic modeling using the NDLib package. So, till now, we have discussed the three popular network models, namely the small world, random, and scale-free, which have no community structure. But in reality, individuals with similar interest or background, they tend to interact more with each other. This is drives the concept of homophily, which is used widely in sociology, describing the tendency of individuals to associate and bond with similar others. For example, homophily by gender is most common in groups. So community rests on the expectation that there exists a densely connected group of vertices with sparse connection to other communities. In real world, communities are full of easy to spot communities. Next, the strength of the community structure, it can be quantified by modularity. So the modularity of a community, it is the difference between the links in a community and the expected number of the links. So as you can see in the bigger bracket, the first term, it gives particular community, and the second part, it denotes the expected number of links that a community can have. So the difference between the two, it gives the modularity for a single community. So summing up the modularities for all the communities NC, we get the modularity of the entire network. So high positive values of modularity, they indicate the presence of a community structure. Communities in real world networks. In social networks, people tend to form groups based on common interests, same profession or background. For example, employees of a company are more likely to interact with their co-workers than with the employees of other companies. So another example is communities could also represent circles of friends or individuals living in the same neighborhood. In a citation network, the vertices in a graph, they represent a paper and the edge represent the paper towards its sides. Another example is the World Wide Web, where web pages that are on the related topics, they form a community, co-author networks, etc. So identifying communities in networks, they help us in understanding the epidemic dynamics better. Creating networks with community structure. So stochastic block model, it is one of the most popular networks with community structure. It was developed by Holland et al. In 1983. Stochastic block model, it gave rise to other popular benchmark graphs with community structure, such as the Girvan and Newman benchmark, LFR benchmark, and ABCD benchmark. So in the Girvan and Newman benchmark, they create equi-sized communities. It was given in 2002 and followed by Girvan and Newman benchmark, LFR and ABCD benchmarks. They're an extension of this Girvan benchmark, where the community sizes, it is based on the degree distribution. So I will be covering stochastic block model in brief. So it is a simple generative model of a random network with community structure. Here the probabilities are specified for both intra-community, that is for any pair of nodes that belong to a community, and inter-community for any pair of nodes in two different communities. So it takes into account the following parameters: the number of vertices, the number of communities, the size of each community S, and a H probability matrix P. It is a symmetric matrix where it is a K cross K symmetric matrix where the diagonal values, they represent the intra-community connections, and the non-diagonal values, they represent the inter-community connections. Example. So in the following example, I have created a network of 90 nodes with 3 communities. So in the following example, this is 3 equi-sized communities. So the vector S takes values 30, 30, 30. That means first community has size 30, second community is also of 30 nodes, and third community is also of 30 nodes. This is the probability matrix P. So the diagonal values 0.3, it shows that in community 1, any 2 nodes are connected with probability 3. And the non-diagonal values, for example, row 1 and column 2, it shows community 1 and community 2. The nodes in community 1 and community 2 are connected with probability 0.02. So since the communities are equi-sized, so we can call this homogeneous SVM. Okay, so the next is the Endlib package. So it is a Python package to model and analyze diffusion processes over the complex networks. It is available for Python 2.7 and 3. And it is built upon the network facilities offered by NetworkX, which is another Python package. So I will be giving the demo in the Google Colab. Is my screen visible, readable?
Yes, Kirti, it is visible.
So Colab is a free Jupyter notebook environment that runs entirely in the cloud. You can write, execute code in Python. Also, you can document your code and create, upload, and share notebooks with others. In the following example, we will learn the basics of the library, describing a simple SIR model. So as a first step, we will see how to install the library. And we will install the library using the pip command. So pip stands for package installer for Python. You can run the command using this run cell. Now your package is installed. You can check if it is correctly installed by importing the package. Import package name. So it is correctly installed. So the simulation, So the simulation workflow, it is divided into 4 parts basically. So first we create a network that can be used as a playground to study the diffusive phenomena. Then we select the epidemic model and the parameter setting. Next, we execute the simulations and visualize our results. So we'll first see how to create a network. So we have created, we create a simple random graph, also known as Erdős-Renyi graph. So we can generate the Erdős-Renyi graph using the NX. First we import the networkx package, import networkx as NX. NX can be used as the alias. The Erdős-Renyi graph, it uses 2 parameters, N and P. N denotes the number of nodes in the network and P denotes the probability for edge creation, that any 2 nodes in the graph, what will be the probability that they form a connection. So here we create a network of 500 nodes with edge probability 0.1. Next, we can see how to visualize this graph. We can use another facility by networkx, that is the draw function. It uses the graph object G and we can set the node size accordingly. So as you can see, there are 500 nodes in our network and the edges are given in black color. We can also see if we can reduce the probability. So you can see the edges have reduced as the probability of edge creation reduces. So after we have created the network, the second step is to select the epidemic model and do the parameter setting. In our example, we import the SIR model and instantiate it on our graph. So the SIR model, it is available in the submodules model. The submodule is model and the submodule is epidemic. So SIR model, it is available in NDLib package with the alias name EP. So every model, it has its own parameters, which can be seen by accessing the parameters field. So we can see, okay, first I run this. So now we have created a model, the SIR model, and instantiated it to the model object. Next, we can see what all parameters the SIR model can take. So as Sharanjit ma'am has told, so the SIR model, it takes beta, that is the infection rate. It is not optional, it is compulsory to give, and its value is between 0 and 1. Next, it takes gamma, that is the recovery rate, and also its value is between 0 and 1. So these 2 parameters are not optional. Next, if we want that the infection rate depends on the number of infected individuals in one's contact, we can set the parameter TP rate as 0 or 1. It is an optional parameter. Similarly, to obtain a list of statuses in the SIR model, we can use model.available statuses. So this gives that this shows that the susceptible nodes, they are represented by the status 0. The infected nodes are represented by status 1, and the recovered nodes are represented by status 2. Next, so after selecting the diffusion model, we configure our model by setting appropriate parameters and initial infection. NDLib offers a common interface to specify the parameters. The submodule, this submodule, model config, it takes care of validating model parameters. First, we create a configuration object. We create a configuration object, CFG. Then we add our model parameters, beta and gamma. So here I have said beta is 0.001 and gamma is 0.01. This can be varied as per the pathogen. We also set the initial fraction of infected individuals by using the initial infected percentage, and we can set the initial status of the model using this configuration object. So first I'll run this. So we have added the parameters beta and gamma to the configuration object CFG. Next, we also set the percentage infected and initialize. So this shows we have infected 1% of the population and marked it as infected. So once we have described the network, the model, the parameters and initial conditions, we perform the simulations. So in NDLib, each iteration, all nodes in the network are evaluated and their status are updated according to the model rules. In order to execute the simulation one or more times, the iterations must be required using the model.iterations. The iteration is a submodule. Or you can also specify the number of iterations. If you want to run it for one or more days, you can call the iteration bunch function, where n bunch denotes the number of days you want to run the simulation. So for example, in our simulation, we run it for 100 days and we call model.iteration bunch for 100 days. Now you can print and see. So the status returned by the iteration bunch, it is incremental. Each iteration describes the configuration of the nodes in network that change their status from the previous iteration. So we can see the iteration number, that is on day 0, there were 495 susceptibles. We have said 1% of them were infected. So infected are 5 nodes and none have recovered. On day 1, same status. On day 2, 1 more got infected. So the susceptible population reduced to 494, infected increased to 6, and there were no recoveries. So we run this. So we had run this for 100 days. So you can see how the infected, susceptible, infected, and recovered. The number of nodes in each compartment changed over time. Next, we can transform this data into diffusion trends using the build trends function. Next, we will print these trends and see how our data returns. So as you can see, so I'll show it from here. For example, the iteration, we got it on day 0. What is the status of nodes in susceptible, infected, and recovery? So the trends return it column wise, 495, 495, 494. So how the susceptibles changed over time, how the infected changed over time, and how the recovered changed over time. That is returned by the build trends function. So you can see it will be for 100 days. So once we have simulated the epidemic spread, it's time to visualize our results. NDLib has defined a visualization package, the diffusion trend, which uses the model configuration and the iteration results that we computed above to plot the simulation results. So we call the diffusion trend function and plot our results. Actually, the probability was lower, so maybe I could change. I can change my network with high probability and see better results. So the figure shows the x-axis shows the iterations, that is the number of days. So we ran our model for 100 days. X-axis shows the number of days and y-axis shows the number of nodes in each compartment. So in the SIR model, there are 3 compartments: susceptible, infected, and removed. So the blue line shows at time 0, there were all the nodes were susceptible. So the trend decreases as the infection spreads, and similarly the recovered individuals also increase. You can visualize your plots here.
Yeah, Kirti, can you rerun this using different beta and gamma?
Yes, ma'am.
Take larger value.
Yes, ma'am. So here.
Yeah. Yeah.
So here I've taken beta as 0.01, so I can change it to suppose 0.1, and gamma I can take higher value.
Yeah, beta you take as 0.2, recovery you take as 0.1. The same parameter we have used in simulation.
And I'm taking percentage infected as 1% only. Running it for 100 days.
Do you mean only 1% infected people?
Yes, ma'am. We can set how many individuals are infected at time 0. For example, you can assume 1% is infected, or you can assume only 1% is infected. It depends.
We can vary that in simulation. So you first show the effect of beta, changing beta and gamma for a couple of combinations. Then we can go to this weight parameter also.
I will have to create the model again. Sorry. Like now configure, initialize, for iterations. So you can see the change here only. in the previous, we saw none of the susceptible was decreased on the day 1. You can see most of the susceptibles are now infected. 45, it increased from 5 to 45. So this is because of the high value of beta. Okay, we can see further. Is the graph visible?
Yes, it
Yeah,
is.
yeah, it is. Yeah, it is.
So as you can see, since the value of beta was very high, so in the beginning of the epidemic, I think around 10 or 15 days,
No, I
almost
think
all
3 or 4 days only, it became 0.
Yes, ma'am. Susceptibles became nearly zero, and most of them recovered then. So this is because of the high value of beta and high value of recovery. So NDLib also provides implementations for other epidemic models, such as the SI, SIS, SIR, SE, IR, all the general models. So another common goal is to perform the comparison among different models. To address this, NDLib provides visual comparison plots. First, we execute a second model, SI, over our original random graph. Similarly, we create another model using SI model, configure it, add model parameters, set the initial status, and run our model. So the multi-runs, what it does, it allows parallel execution of multiple instances. So in the above example, we have just run one, we have not done the multiple iterations, we have just done the one iteration. So you can do multiple iterations using the multiple runs. So we can compare this SIR model and the newly created SI model using the trend comparison. Another submodule that is provided by the NDLib package. So in the trends comparison, we pass both the models and both the iteration results, that is the trends of the SI and SIR model, and we print the infected nodes, the trend of the infected nodes. So as you can see, since the SIR model, the beta was quite high. So in few days, most of them got infected and then they recover slowly. In the SI model, the beta was quite low, 0.001. So infection spreads slowly. And this light color, since we have used the multi-runs, that is, we have run the model for 10 iterations. So this shows the variance of the results. Here we have compared only the infected individuals. You can also compare the susceptible and recovered by changing this status. So here I've shown an example. For example, we also want to compare infected and susceptibles. You change the status parameter and plot the results for SI and SIR models. So here you can see the trends for infected and susceptible for both the models. Ma'am, this is all that I have covered in the demo part.
So we can take questions.
Kirti, could you explain once this graph, the difference between SI and SIR in this graph?
Yes, ma'am. Ma'am, so the values for SIR model, we have used beta as 0.2 and gamma as 0.1. So they were quite high values. So in the beginning of the epidemic, as you can see, dark blue color represents the infected individuals and light blue is the susceptible. So at time 0, all the individuals were susceptible with few infected individuals. So as time progresses, the susceptible individuals reduce as the infected individuals peak. So this shows the trend of susceptible and infected over the time. Similarly, as you see the orange curves, dark blue color curve, dark orange color shows the infected individuals. So as it is expected that initially susceptibles will be high and infected will be low. And as time progresses, infected will increase and the susceptible will decrease. So they'll have a opposite trend.
Yes, right.
Kirti, can you compare this with the same probabilities, beta and gamma for both? So now actually, the probabilities are so different that the comparison isn't very stark.
Yes,
yeah. So don't make it 2. 2 is very high, it seems. Make it little smaller for both. But make it
SIR model again.
yeah.
Ma'am, what value should I take? 0.1 maybe.
0.1 ले लो, इसे 0.05 कर लो.
First, I'm running the SIR model. Running it for 100 days. Maybe I can show the comparison. The probability is still high. So in the SIR model, the infections, most of the individuals are infected during the initial phase of the epidemic, and once they recover, the infected individuals decrease over time. And since in the SI model, the epidemic reaches the endemic state, that is, all the individuals, once they get infected, they do not decrease. All the individuals are infected at the end. So you can see the orange line at the top. This shows the endemic state in the SI model.
So Kirti, you can also show here the role of average degree of the network which you have plotted. So that will also have the impact. Now, if there is a time, then we can do this.
Okay, so I can
construct network in the beginning when you constructing that. Yeah.
So here I've taken the probability of edge as 0.1. So if I take more number of contacts, or maybe reduce this, reduce the number of contacts. So we can see the graph has shifted to the right. So the number of days in which all the individuals are infected, it has increased. So the graph has shifted to the right when we decrease the number of contacts in a network. So the degree is an important factor that plays an important role in the epidemics.
Yes, I hope quite understandable. And Miss Kirti, could I ask, this is your PhD work?
No, ma'am, this is not my PhD work.
Okay.
We have used epidemic modeling, but this is not my PhD.
Okay. You'll be presenting one of your works at IHIC also, right?
Yes, ma'am. Yes, ma'am.
Okay.
That is part of her PhD thesis.
Okay. If the audience has some questions to ask, you could please proceed. We are towards the end of the tutorial now. Fine, Vasudha ma'am, Sharanjit ma'am and Kirti.
Thank you,
It
ma'am.
was very informative and we really enjoyed a lot. We relished it. And it is really useful also actually. And people doing research in this field could definitely make a impact and use the model, the SIR model that you proposed.
Thank you for giving us an opportunity. So if anyone is interested in working over this, so you can feel free to contact us. So our emails are there. Kirti's GitHub account is there. Anyone can contact if somebody wants to work in this area. So all these models were proposed about 100 years back. But they have been extended depending on the new, the advancements in medical science, there's advancement in mathematics, all these. So Kirti is working on modeling different aspects.
Of epidemic only.
Of epidemic, yeah.
Okay.
But people interested in social network analysis or social media analytics, diffusion of information over the social media networks. For them, these models are again very important. But these are very basic models. There are much more sophisticated models which are used.
Okay.
These models are also used to find out where the rumors started or who is likely to spread the rumor. So there's a lot of interesting there are a lot of interesting problems in this area.
Yeah, actually, I am a novice, I should say, in this field. So I haven't come across these models. So it was really interesting for me, at least.
Oh, thank you.
Yeah, and the presentation, the way it was presented was also wonderful. So I really understood it.
Thank you.
Yeah. So thanks to the speakers, thanks to Sharanjit ma'am, thanks to Vasudha ma'am, Miss Kirti. It was a wonderful presentation. Thank you everybody. And as soon as we get the recording, we will send you the recording as soon as possible. Yeah. Thanks for being here. Thank you very much. So you're welcome to attend the conference sessions also, whenever possible for you.
Right. Thank you very much.
Yeah. Okay. Thank you.
Bye.
Bye-bye.
Bye.
Bye, everyone.
Bye.
Bye-bye. Thanks for the wonderful audience. Bye-bye.
Yeah, thanks to the audience.
Thanks a lot.